Okay, so thank you everybody for being here. So today I'm gonna present my paper. We'll start with this causality versus zero correlation in asymmetric Portmanteau test. Okay, so the motivating context is the following. We're trying to understand how, so from the economic perspective, how does economic uncertainty impact some target variable of interest? So for instance, we're talking about inflation or stock market returns. So common practice in macroeconomics is first to specify a structural dynamic model through which basically we identify exogenous variation that we label as shocks, and in this case, uncertainty shocks. And then we investigate the propagation of these shocks through the dynamic system, eventually understanding the causal impacts of these shocks. In other words, we are running impulse response analysis. So the underlying assumption behind impulse response analysis, though, is that the shock needs also to be exogenous, not just internally, but also externally, with external variables that are omitted from these structural dynamics. So I will refer in this talk as X as our shock series and Z as the external variable. So this translates into the following econometric question, and then we are keen on understanding whether the shock are really exogenous fluctuation associated with uncertainty. And in this case, it boils down into checking the following two conditions holding all together. The first one is that the shock needs to be exogenous with respect to the past of the internal variable, in other words, whether the model is enough correctly specified. And secondly, whether the external variables do not influence the exogeneity property of the shock. And the second part is the focus of today's talk. And basically, we are keen on testing whether the past of omitted variable predicts or not the presence of uncertainty shock. So, okay. So to put some math on the table, so hypothesis of interest is conditional mean independence, okay, of X, so our shock at present time, conditioning on its own past and the past of these omitted variables. The alternative will be basically the model is roughly correctly specified, and the omitted variable though influence the exogeneity of the shock. So among all the class of testing procedures that might be considered, I'm starting with the plain vanilla types that are building on the serial cross-correlation function. So in this case, we are considering the correlation between the lagged and past omitted variables and the present localization of the shock. So among all these zoo of testing procedures, those can be classified into two different approaches, essentially. So either we bring this omitted variable inside the model, so we parameterize, so the past of the impact of past omitted variables onto the present of the shock and also the vice versa. So we have full parameterization, and we can run our wall tests, okay, for instance. And those tests, again, require correct parameterization to work. The second type of test do not require augmentation, so we just start checking in a non-parametric fashion, but the problem there is that usually those tests are characterized under the null hypothesis of mutual independence. So in a way or the other, basically the conclusion about exogeneity of shock might depend eventually on the causality that is inverse of the one being tested, namely the impact of past shock to present of emitted variable. And this can cause size distortion. So this paper, what do I do is study a very complex problem of model specification testing, dynamic model, in the presence of omitted variables. In particular, what I do is I propose an asymmetric Portmanteau statistic to test exogeneity. So Portmanteau statistic is weighted sum of square sample cross-correlation and all lags. And the asymmetric part is coming by the fact that I'm adding this correction term to the Portmanteau statistic that offsets the part of the statistic that is capturing this inverse causality. As a byproduct, I don't need to model the joint dynamics, and it can be thought to be, my statistics will be robust to potential misspecification of this inverse causality channel. So as an econometrician, as an econometric contribution, I establish the asymptotic normality of the corrected statistic. And as an empirical contribution, I test the exogeneity of proper measure of macroeconomic shocks. And if we're lucky today, we will be covering the EPU shock, so economic policy uncertainty shock of Baker Boom days 2016. Spoilers alert, is not exogenous. And hopefully I will try to convince you about the consequences of the endogeneity coming from revisiting a paper of Dirksen in the morning. So very, very simple setting. So in the paper, I'm adopting a more generalized setting, but let's stick to this with this presentation. So we have X and Z. So again, X, you need to think about it as the shock, Z as our omitted variable. 2, 0 means standardized univariate jointly stationary processes. Null hypothesis is conditional mean independence or marking the difference property of X with respect to the joint information set. The building blocks of our statistic will be cross-correlation function, so linear association. And then the benchmark test, my starting point, is a one-sided sum of weighted square cross-correlation at all lags. So in this case, you can clearly see the omega are the non-random, non-negative weights. And you need to think about them as coming from a kernel function. Okay, and those are indexes by J, because essentially the width of the kernel or the number of non-zero weights will be increasing with the sample size. So now so these two slides, they are following this one, and the next one will be basically the key point of the paper. So you need just pay attention to these two, and then you're done. So essentially, symmetry of squares. So squaring of cross-correlation induces cross-product terms at varied time indexes. Meaning, in other words, that if we think about like the simple algebra, a plus b squared, we'll have a squared plus b squared plus 2ab. In other words, sum of squares and sum of cross products. As we are squaring the cross correlations, then essentially the benchmark test statistic can be decomposed in a similar way. So we'll have a sum of squares and a sum of cross product part, T1 and T2 respectively. In the first part, notice that Z always happen, so the time ordering of Z is always preserved with respect to X when we're considering the causality we are testing. So Z is always happening before X. Whereas in the second part of the statistic, we will have an additional time index, that is S. And in this case, we will have that, as we know, the L2 norm of squaring treats everything symmetrically, we will have that for some combination of S and T, right, given J, we will have that X is happening after Z, and for some is happening before Z. So if we suspect that there is some inverse causality captured by this statistic, then the first subset will be the sum of cross products. Then, okay, so I'm adding more log in the fire. So let's talk about the asymptotic property of the benchmark test statistic. In this case, the two parts are basically playing different roles in shaping the properties of the statistics. So the first part, T1, dominates on the alternative, so in other words, control for the power of the test. Vice versa, the sum of cross products control for the size of the test. So when I was talking, I was referring about size distortion because of inverse causality, everything points out to the sum of cross products. So let's check the second order property of the cross terms. So essentially, proposition 1 is telling us that there might be some problem. So under very, very stylized assumption, so X and Z being marginally ID univariate with finite for the moments, okay? So if X is independent of past Z, right? So in this case, we are strictly under the null hypothesis, okay? The variance of the cross products can take two different values. Can take value 1 when we have a specific combination of S and T given J, or can take a complex value, a high order moment that is basically capturing this inverse causality I was mentioning about. And now you should have asked me, look, Amedeo, but like before you were telling me this kind of test, these Portmanteau tests are characterized under mutual independence. What's happening when we have mutual independence then? Then the second part of proposition 1 is telling us that the variance of the element of the sum of the cross products is actually taking value 1 under mutual independence. So the benchmark test essentially what is to take from proposition 1 is just the following. So the benchmark test via T2 incorporates inverse causality, unless we have one of the two conditions play. Either mutual independence, which is not the focus of today's talk, or a specific time ordering is met. So in this case, my approach is simplistic in nature. So the correction term is a difference in, so what I propose to apply a correction term that difference out the terms, the cross products that are capturing this inverse causality. and remove part of the statistic that is associated with a particular value of S and T. In other words, you can think about either I'm subtracting a correction term, or I'm correcting, or I'm just considering part of the second part of the statistic. Notice that in the decomposition, though, the first part of the statistic remains untouched. In other words, I should have better size property and same power of the original test statistic. So under the null hypothesis, so that's theorem one. So I will briefly mention a bit of notation. So IT is the information set available at period T, okay, of the joint times here, so the augmented sigma algebra. Then we will have our assumption one, weighting function. So first line of assumption one is telling you just that basically the weight, the non-zero weights will be growing with the sample size. And the second line of the assumptions tell you that basically those are associated with a kernel function that is square integrable and so on and so forth. So other people here presented like non-square integrable kernels, so we can talk later about it, but that's the assumption at the moment. Then let's talk about theorem one. So suppose that X is conditional homoscedasticity, is conditional homoscedastic and conditional homocortic. So I know that that's a strong assumption, but I will discuss later on. So suppose thirdly that the time series Z is for the stationary, nice finite order moments, and we have strict stationarity of the joint process. Then under assumption one, and a particular ratio between the number of non-zero weights and the number of the sample size, okay, we have that the standardized statistic converges to a standard normal distribution. I know it's a lot to take from the conditional homoscedasticity and conditional homokurtosis, but let me kind of like provide a bit of context. So in this case, the restriction of conditional moment, the first one is actually necessary if you wish to isolate the center of the statistic with respect to the variance of the cross products. So essentially, it's a byproduct of squaring, and so that's why we need to place some conditional, so some restriction on the variance. Regarding the conditional homokurtosis, basically, it's just like to have a nice central limit theorem. Regarding the homoscedasticity, we can think about it also as applying like say, a Garch model or like something that fits also the variance, so that basically we have that condition almost automatic. So I provide additional results in the paper. So with like a number of non-zero weights is like the ratio between number of non-zero weights and sample size is a bit better. I provide also in this case results when basically we are estimating these processes instead of directly observing our X and Z. So let me jump directly to the empirical application. I think I'm doing fine with time. Anyway, so in this case, the shock I'm considering will be the EPU uncertainty shock. This is coming from the Economic Policy Uncertainty Index, which is Baker-Bloom-Davis 2016 paper. It was actually one of the first that was using monthly frequency, was counting and was using text data to build the shocks. So essentially, it's monthly frequency of newspaper article containing uncertainty, economic, and policy, plus some additional indicators. So I replicate exactly the series in order to have our EPU shock. For what concerns our omitted variables, though, you can come up with different type of external variables, but essentially I'm following the Fournier-Gambetti type of approach, 2014, which essentially means that I control for the eighth principle, so from some principal components that should be capturing the state, the state space part of the macroeconomy. In this case, in this example, I'm talking about the first eight principal components of the macroeconomic data set. So what I'm presenting here, so it's a lot to digest, but let's start from the left and then move to the right. So on the left x-axis, we have the width, the number of non-zero weights, okay, and its monthly frequency. So basically, we are considering the different lags, and we're basically it's like 2 years and 2 quarters or something. Then on the y-axis, we have the absolute value of the statistics. Okay, the straight lines, the dash or dot, are the critical values, so essentially at 10 and 5%. And then I'm plotting those like blue and orange line. Those are the test statistics, okay? The corrected is the orange, the blue is the standard. And we can clearly see that as we are progressively considering more and more lags, at least 1 year, basically we are able to reject the null of exogeneity of the EPU shock when with respect to the McCracken-Yang macro factors, okay? And the problem there is that you can clearly see that when we are considering at a certain point, at a certain threshold, when we are considering farther in the past, then we have that the standard test is telling us to actually is failing to reject the null of endogeneity. All right. So in this case, it will tell us that basically the shock is exogenous when we're considering enough lags in the past, whereas the corrected version is kind of like giving us a coherent picture. So when we are decomposing the statistic and we are going on the right part of the figure, then basically we're decomposing the statistic into 3 different parts. We have the conditional heteroscedasticity, so basically the center of the statistic, and then we will have the inverse and the tested part. So the yellow part is T1. Then we will have the blue one is the one that basically remain after the correction, and the orange one is the correction term. And essentially, we can see that the part that is playing a huge role in at the beginning was the inverse causality, okay, and then essentially fades away, right? And that's why the standard test statistic is telling us to reject. It's telling us not to reject after we are evaluating basically enough past observations and correlation. So in this case, I'm proposing. Sorry. Oh.
You might want to go towards the conclusion on this to keep it fair.
Okay. Yeah. I will. Yeah. Sorry. So to be very quick, so I have like here, I propose an example where I basically try to convince you that this endogeneity. So in this case, like what to take from this picture is that basically the shock is not exogenous and we need to correct for these additional principal components. I revisit local projection analysis, right? And then I show that basically so these on the left are the original findings, and on the right the correction. So you can clearly see that basically there is a massive shift in in a particular impulse response analysis related to the effect of uncertainty shock onto inflation. So we can shift from negative to positive. We can talk more later on. And here, just to summarize the results of the testing. So basically, I test for different type of shocks, so monetary, carbon, oil, uncertainty, and it seems that most of the Kanzik shocks resist. And also some part of the monetary policy. Unfortunately, the Bauer and Swanson and the Yaroginski and Karadi, they tend to suffer of heteroscedasticity, whereas the uncertainty shocks, they tend to be suffering of endogeneity due to nonlinear components. Anyway, so to conclude, what I propose here is a strategy to test exogeneity of shocks based on Sear curves correlation. And so in 2 lines, contribution is that I econometrically impose directionality to the Portmanteau statistic through a correction term. And in particular, I offset the size distortion due to inverse causality. And then empirically, I test the exogeneity of EPU shocks by revisiting the Dirksen-Tomoni paper. Bottom lines, squares incorporate inverse causality. So I try to avoid that. So L2 might be dangerous sometimes, and EPU shock are not exogenous, so you need to add additional controls. So I think I shall stop sharing.